Now here the nucleophile will attack the positively charged carbon and ending up getting the product. And here this reaction is the slowest reaction, while this one is the fast reaction. So the rate determining step reaction is this one, the first step. So in the first step we see that only one reactant are being involved. That's why we call it first order nucleophilic substitution reaction. And the first order nucleophilic substitution reaction is enhanced with the stability of carbocation intermediate, which means that this is due to positive inductive effect. So due to positive inductive effect on positively charged carbon, the tertiary alkyl halides will be fast in this kind of reaction than the secondary and the primary alkyl halides due to stability of positively charged carbonium ion, whereby the alkyl group here releases electrons, thereby stabilizing the positively charged carbon. Therefore, the first order nucleophilic substitution reaction is fast in tertiary alkyl halide than in secondary alkyl halide due to stabilization of intermediate carbonium ion. So this is all about the first order nucleophilic substitution reaction. If we consider the second order nucleophilic substitution reaction, which is also known as bimolecular nucleophilic substitution reaction, bimolecular nucleophilic substitution reaction. This reaction is also called as second order nucleophilic substitution reaction. Why is it called the second order nucleophilic substitution reaction? Because the rate of reaction depends on two reactants in rate determining step reaction. And is denoted as what I have said, the rate of reaction depends on the concentration of both reactants, and that is the alkyl halide and the nucleophile. So it depends on the concentration of both reactants, that is the alkyl halides and the nucleophile. Now consider this example whereby you have the nucleophile. So due to weak steric hindrance, the halogens makes the carbon to be positively polarized, while the halogens becomes negatively polarized. So the nucleophile now will attack this carbon and resulting into formation of this intermediate product, which is now called the transition state. So during the transition state, both the reactants are being involved, which differs from the first order nucleophilic substitution reaction, where only one reactant are being involved. So that's why here we call it second order nucleophilic substitution reaction. And there now the reaction will proceed now to form now the halogen now will be substituted by the nucleophile, and so during transition state, during transition step, both the reactants are involved. That's why we call it second order nucleophilic substitution reaction. Now these are the two mechanisms of nucleophilic substitution reaction in haloalkane. And the typical examples of nucleophilic substitution reaction are, we have the hydrolysis, we have formation of ester, we have formation of ether, we have formation of isocyanide, we have formation of alkyl cyanide, and we have the formation of nitroalkane. Those are examples of nucleophilic substitution reaction in haloalkane.
You are watching DARASA Online.
So from there now, I'm sure you are able to describe the nucleophilic substitution reaction in haloalkane by these two mechanisms. Normally, the order of reactivity in the bimolecular nucleophilic substitution reaction follow the trend. Is the alkyl group is greater than the primary alkyl halides. The primary alkyl halides is also more reactive than the secondary alkyl halides, and the secondary alkyl halides is more reactive than the tertiary alkyl halides. So that is the order of second order series in chemical reaction of electrophilic substitution reaction. So from there now, after a short break, we will now see some examples or some questions which might appear in the exam, and once they appear, you can follow this mechanism and get the answer correct. Thank you. Okay, welcome back to our lesson now. As what I've said now, we are now going to look some of the sample questions that may appear in your exams, which involves the use of this knowledge that we have discussed. Now, the first example or the first question is that 2-bromo-2-methyl propane reacts with aqueous alkalis via first order nucleophilic mechanism. Now you are asked to write the chemical equations to show how the reactions occurs according to this mechanism. It is so simple since you have seen how the mechanism is taking place. Then in second, we have been asked to identify the rate determining step. And third, why the reaction is referred to as first order nucleophilic substitution reaction. So by answering that question, let us start now writing the formula of 2-bromo-2-methyl propane. 2-bromo-2-methyl propane, our longest chain is propane, so it has 3 carbon atoms. And to carbon number 2, we have bromine, we also have CH3. So this is, here we have hydrogen, 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 and there we have also hydrogen, hydrogen, hydrogen. Or in simple way, you can write it as CH3, C, then bromine, CH3, CH3. So this is 2-methyl, 2-bromo-2-methyl propane. So we have been told that it reacts with the alkalis. Alkalis, it can be either sodium hydroxide or potassium hydroxide. So let us consider by using potassium hydroxide. So CH3, bromine, CH3, and CH3. And we see that this is tertiary haloalkane. So if it is tertiary haloalkane, that means it undergoes first order nucleophilic substitution reaction, meaning that it involves only one reactant, or the reaction depends on the concentration of only one reactant. So our alkali releases hydroxide ions as the nucleophile, and hydroxide ions is the stronger nucleophile that can substitute the halogens. So our nucleophile is hydroxide. So it will react now, whereby the bond will break down there, and you have the intermediate carbocation, which is this one. This is now the first step. The second step now, the nucleophile, this one will attack now the positively charged carbon. So this will attack the positive charged carbon, then ending up getting the product that will be the alcohol. So this is the mechanism that we have been asked to write these equations. So the second part, we have been asked to identify the rate determining step. The rate determining step here is the one which is the slowest step. And which of the two steps is the slowest step? This one is the slowest step. So this is the one which determines the rate determining step. So the rate determining step is the first step mechanism. So let's say that this is the first step reaction, and this is the second step reaction. So to determine the rate determining step, you consider the slowest reactions, and this the second one is fast. So that is the answer for the second part. But the third part, you have been asked to explain why the reaction is referred to as the first order nucleophilic substitution reaction. So the reaction is referred as to first order nucleophilic substitution reaction. I'm sure you can answer it because we have explained it when we were talking about the first order nucleophilic substitution reaction. So here it is the first order nucleophilic substitution reaction because the rate determining step, or the rate of reaction, depends on only one reactant, or depends on the concentration of one reactant. And what is that reactant? Is the alkyl halide reactant. So that is now over about that reaction. Do you see now? It is very simple after having that knowledge. So let us go and see the second example. In the second example, we are now asked, we have a question which states that a compound A contains 66.4% carbon, 5.5 of hydrogen, and 28.1 of chlorine, and the vapor density of empirical formula of A, the molecular formula of A, and the write down the isomers of compound A that can exist and their names. Which of the isomers mentioned in B can react with dilute aqueous potassium hydroxide, and why the other isomers cannot react with aqueous potassium hydroxide? And you have been given the atomic mass of carbon, which is 12, hydrogen, which is 1, and chlorine, which is 35.5. Now, by just the highlights, our compound contain carbon, hydrogen, and chlorine, which means it is a haloalkane because there is carbon, there is hydrogen, and there is chlorine. So to answer the first part, let us construct a table. That the compound contain carbon, contain hydrogen, and contain chlorine. The percentage of carbon is 66.4, and that of hydrogen is 5.5, and that of chlorine is 28.1. Now, we have been given their relative atomic mass. So the atomic mass of carbon is 12. So we have to divide the percentage by the atomic mass of each element. So here we'll divide by 12, and here we'll divide by 1, and here we'll divide by 3 by 35.5. Now, by using your calculator now, you can find the ratio of these data that you have been given. Data into your calculator, 66.4 divided by 12, the answer is 5.53. And here will be 5.5, and there 28.1 divided by 35.5, the answer is 0.79. So here now we divide by the smallest ratio, which is now 0.79. So here we'll divide by 0.79, here by 0.79, here by 0.79. Now after dividing it, divide it using your calculator now, 5.53 divided by 0.that1, then you get here 7. So here will be also 7, and this will be 1. So what does it mean here? That we have 7 carbon atoms in our haloalkane, 7 hydrogen atom, and 1 chlorine atom. So the empirical formula now, the empirical formula will be equal to C6, C7, and then hydrogen 7, and 1 chlorine atom. And the second part, we have been asked to determine the molecular formula of A, but we have been given the vapor density of our compound. So from that now question 2, we know that the empirical formula times N is equal to 2 vapor density. And our empirical formula is C7H7, then 1 chlorine, times N will be equal to 2 times vapor density, which is 63 given in that equation. So here it will be 7 times the carbon is 12, then plus 7 times 1, then plus chlorine is 35.5, then times 1 also, then in bracket times N will be equal to this one, gives the 126. So if we substitute into our calculator 7 times 12, then equals to 84, then plus 7, then plus 35.5, the answer is 126.5 N. So it will be equal to 126. So divide by 126.5, then 126.5. Now the answer, therefore, N will be equal to 1. Therefore, the empirical formula is the same to the molecular formula. Then the molecular formula is C7, then 7 hydrogen atom and 1 chlorine atom, since the value of N that we have obtained here is 1. So that is the first part of our question. Now the second part, you have been asked to write the isomers of compound A that can exist in their names. Normally, by looking the molecular formula, you can know the type of halogens derivatives of our compound A. And here, since we have 7 carbon atoms, it means that our halogens derivatives of hydrocarbon contain benzene ring or the aromatic ring. So from there now, to draw their isomers, the isomers now of compound A that can exist in their names. So our isomers must have 7 carbon atom, 7 hydrogen atom, and 1 chlorine atom. The first isomer might be this one. Which is known as chloro methyl, then benzene. If you count the number of hydrogen is 7. 1, 2, 3, 4, 5, 6, 7. Carbon 1, 2, 3, 4, 5, 6, 7. Chlorine 1. So it match the molecular formula that we have obtained. Now the second isomer can be this one. Which is known as 2-chloro-methyl benzene. So this is 2-chloromethyl benzene, but there are 7 carbon atoms, there are 7 hydrogen atoms, and 1 chlorine atom. But also another isomer can be this one. And this is 1, 2, 3, 4. This is 4-chloro-methyl benzene. And also another isomer can be this one. This is 3-chloro-methyl benzene. So from the mentioned isomers, we have been asked which one will react with the potassium hydroxide. If you refer now to our nucleophilic substitution reaction in halogens derivatives of hydrocarbon, this one is the one that can react with the aqueous potassium hydroxide. Why? Due to presence of alkyl halides in the molecule. So here is where now the hydroxide ions that will be released by potassium hydroxide, which is our nucleophile, will now substitute the halogens here. But in the remaining
Sasa mnafanya kazi nzuri sana. Kwa hiyo salamu hizi nitazipeleka kwa wazee wenzangu, Mzee Karume na Mzee Kawawa, kuwaeleza kwamba sasa angalau kivuli changu kinaishi Tanzania. Yale yote niliyokuwa natamani yafanyike sasa yanafanyika chini ya serikali ya awamu ya 5 inayoongozwa na kijana wangu John. Kwa hiyo niwaache wajukuu zangu, muendelee kulijenga taifa letu tukufu la Tanzania.
Ni wajibu kumshukuru Baba Nyerere kwa furaha, shangwe, pia vigeregere.
Mwalimu babu yetu tunakukumbuka, Mwalimu baba yetu tunakushukuru.
Ni wewe uliyeleta amani Tanzania.
Ni wewe uliyeleta upendo Tanzania. Asante.
Celebrates.
Ukichukua mkaratusi unatakiwa kwanza uchemshe pamoja na majani ya mchaichai, kwa sababu majani yake ni magumu. Maji yakishachemka ndipo unachukua kivumbasi. Kuna vivumbasi vya aina nyingi, lakini kivumbasi ambacho kinapatikana kwa wingi ni kile kivumbasi kidogo au kashwagara au mweni ndogo kwa lugha za kikabila kwa zile kanda ya ziwa na hapa pwani. Kwa hiyo hizo ukishazichukua jifunike, lakini nataka nitoe tahadhari ya jinsi ambayo uweze ukaumia. Kwa wale ambao ni watoto wadogo chini ya miaka 3 tusiwafukizie, na wale ambao wana kifafa usiwafukizie, na wazee sana ni lazima wafanyiwe kwa uangalifu, kwa sababu wakati mwingine wanashindwa kupumua. Akina mama wajawazito pia wastahili kufanyiwa, na wale wenye pressure haipaswi kufanyiwa. Sasa hata kwa wale ambao wameathirika na mapafu yameshaathirika sana, tunashauri kwamba wanaweza wakafanyiwa ufukizio kwa muda usiozidi dakika 2. Anapumzika, anafukizwa tena, anapumzika, asifanyiwe mfululizo. Hawa ni kwa wagonjwa wa corona ambao wameshaathirika sana, yatakiwa wafanyiwe huku anapumzika. Lakini kwa yule ambaye hajaathirika, anaweza akafunikwa na akakaa kwa dakika 10 mfululizo, na hii ifanyike mara 3 kwa siku. Lakini napenda nipendekeze kwenu pia chai ya moto, ambayo nayo nitatoa tu vitu vichache mnazoweza mkatumia. Ya kwanza ni mlungulungu, ziko Kariakoo, nenda ununue unga wake.